Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
Noether's theorem, the hidden force behind modern tech. You've probably heard of Einstein, Newton, or even Hawking, but have you ever heard of Emmy Noether? Her name might not be as famous as these giants, but her theorem shook the very foundations of physics. Einstein once called her the greatest woman mathematician, and her work became an indispensable part of modern physics. So, what exactly did Noether do to earn such high praise from Einstein? Well, she didn't just scribble formulas on paper. Her theorem, Noether's theorem, revealed the deep connection between symmetries and conservation laws in the physical world. It may sound complicated, but in reality, Noether took Einstein's ideas from good to perfect. She explained why we always see conservation laws like the conservation of energy, momentum, or even angular momentum behind what seem like simple physical phenomena. And the crazy part? There's a deep mathematical principle at work behind it all. But this isn't just for math geeks. Noether's theorem revolutionized physics, offering an essential mathematical framework for quantum mechanics, particle physics, and even relativity. So, the next time you're watching a particle accelerator or casually talking about quantum computing, remember, Noether's formula might already be part of your daily life. You might not know her name, but her theorem runs through almost every branch of modern physics. That's right, Emmy Noether, through one groundbreaking formula, became the unsung hero of quantum mechanics, particle physics, and relativity. Even though she never won a Nobel Prize, she never did. In fact, her legacy is irreplaceable in the history of science. And if you think Noether's theorem only matters to physicists, think again. Her work touches almost every aspect of our daily lives, from the quantum computer you're using, to the smartphone in your hand, to the GPS system you rely on. So, let's dive into the story of this invisible hero of science and see how she changed the way we understand the world with her formula. Emmy Noether was born on March 23, 1882, in Bielefeld, Germany. Her father, Franz Noether, was a well-known math professor, and her mother, Helene Noether, was a homemaker. From the very start, Noether grew up in a household rich with math, with her father being a respected figure in the local academic community. Little did anyone know, this would lay the foundation for her extraordinary future. Even as a child, Noether showed a deep fascination with math. Back in those days, education for women in Germany was limited, especially in fields like math, which was seen as a serious discipline. But Noether wasn't held back by these gender norms. While her father was a prominent academic, he never enforced the societal expectation that women should stick to more appropriate subjects. Instead, he encouraged her to pursue her interests, especially in math, and provided her with all the support she needed. Noether's talent was evident early on. She loved discussing algebraic equations with her father and could solve problems that were far more complex than those of her peers. By the age of 13, she had already mastered the basics of algebra and was teaching herself more advanced concepts. In a way, Noether spent her childhood immersed in the world of mathematics. But Noether's journey was far from smooth. In the late 1800s, the German education system was designed almost exclusively for men. Women were usually relegated to roles in family management or the arts, with fields like math being considered off-limits. Despite her exceptional intellect, Noether had to face immense social and institutional prejudice. Society believed that women weren't suited for logical, abstract disciplines like math and physics, and their roles were expected to revolve around gentleness and family. However, Noether's father remained her unwavering support. Even though the social environment was filled with prejudice, Professor Franz Noether not only provided her with a wealth of mathematical books but also encouraged her to continue learning and diving deeper into the subject. This family support was crucial in laying the foundation for Noether's future academic career. Throughout her academic journey, Noether never let gender barriers define her. Despite the biases she encountered in universities and academia, she stuck to her passion. Thanks to her father's backing, she was exposed to higher-level math theory early on and developed a strong interest in abstract algebra. In those days, there were almost no women attending universities in Germany. Women's access to higher education was severely limited, and in many cases, universities even banned women from entering subjects like math and physics. Noether, though incredibly gifted in mathematics, still had to overcome significant social obstacles and academic prejudice. Each step she took was a challenge against the prevailing gender biases of the time. But Noether didn't give up on her love for math. The strong support from her family kept her going, and she became more determined to push through all the challenges. Though her path was filled with difficulties, she never wavered. Her resilience and dedication laid the groundwork for the remarkable achievements that would come later, proving that even in a world full of gender bias, women could carve their own academic paths. Noether's journey in overcoming these barriers paved the way for her future scientific accomplishments and influence. Even though she wasn't widely recognized in her time, her talent and determination planted the seeds for her academic success. Emmy Noether's journey from an ordinary student to a legendary figure in mathematics wasn't exactly a straight path, it was more of a twist and turn kind of adventure. Her story feels like something out of a math geek's dream, full of challenges and roadblocks, but with each hurdle came the potential to change the world. Let's rewind to 1903. At just 21 years old, Emmy Noether walked into the halls of the University of Göttingen, one of Europe's most prestigious universities at the time, a dream destination for mathematicians. You might imagine her academic career was all smooth sailing from here, but nope, that wasn't the case. Initially, Noether studied both math and linguistics. Why? Because, back then, women had limited educational choices, and safe options like linguistics seemed to be the best route. But Noether wasn't the type to settle for safe. Before long, she shifted her focus entirely to mathematics, particularly algebra and analysis. It was like a magnetic pull she couldn't resist. Math was her puzzle, and she was the one determined to solve it. After all, math wasn't just about numbers and formulas, it was full of beautiful logic and symmetry, and those abstract concepts were what really drew her in. At Göttingen, Noether faced her first major challenge, her gender. In an era when women weren't commonly seen in academia, especially in male-dominated subjects like math, this was a huge obstacle. Most of her classmates were men, and as one of the few women, she often found herself sidelined. Imagine her quietly packing up her books after lectures while the guys gathered to discuss important math problems. But Noether's brilliance and unwavering dedication quickly made her stand out. Her sharp mind could easily grasp complex mathematical concepts, and soon, her research focus became clear: algebra. She developed a deep interest in algebraic equations and group theory, especially in how abstract mathematical methods could solve real-world problems. This was the beginning of her mathematical adventure. In 1907, Noether earned her PhD with a thesis titled Invariance in Algebraic Equations. While the paper didn't cause an academic storm at the time, it laid a solid foundation for her future accomplishments. In it, she explored the mathematical properties of invariance in algebraic equations. Though her name wasn't widely known yet, her work was already offering new perspectives on complex problems in mathematics. At that point, her work didn't spark much discussion in the academic world. Back then, female scholars often didn't get the recognition they deserved, and there were always lingering doubts about their contributions. Even at Göttingen, she couldn't immediately land a formal teaching position. You can imagine the whispers, can she really do math? But Noether, with her sharp mind and determination, slowly but surely pushed through these biases. Though her breakthroughs might not have made headlines back then, her drive to uncover truth was already setting her on the path to greatness. The real turning point came in 1915 when Noether received an invitation from two of the greatest mathematicians of the time, David Hilbert and Felix Klein, to work as a lecturer at Göttingen University. This was her official entry onto the world stage of mathematics. It was more than just a professional milestone, it was the moment she truly became part of the mathematical elite. At Göttingen, she not only collaborated with Hilbert and Klein but also got to engage with them on deep mathematical problems, a huge catalyst for her academic growth. Even then, Noether still faced significant challenges. In a male-dominated academic world, she not only had to prove her mathematical prowess but also had to deal with constant doubt and skepticism from society and academia. Picture Noether, one of the few women in a sea of brilliant, radical thinkers, holding her own in those intellectual discussions. While her contributions were starting to show, she had to work harder and be braver than most of her peers. Despite all the obstacles, Noether's name started to gain recognition in academic circles. Not only did she earn respect for her own work, but she also paved the way for future female scientists. Her path was anything but smooth, but each step was driven by unwavering determination. Her breakthroughs in algebra and group theory laid the groundwork for her rise to legend status in the math world. And all of this began at Göttingen University. What might have seemed like just another university became the launchpad for Noether's brilliant career. It was there that she encountered not only many of the greatest minds in mathematics but also her destiny. Her unique journey into the world of math was just beginning to shine in a way no one could have predicted. If you're watching this video right now, you might be feeling like you're just another unknown in the crowd. Well, Emmy Noether could be the inspiration you need to keep going. She didn't start out with the spotlight on her, but she found her moment of greatness, even when few were paying attention. From 1915 to 1918, Noether's academic journey took a pivotal turn. This was when she began her groundbreaking collaboration with David Hilbert and Felix Klein, two of the most renowned mathematicians of the time. Imagine being a young math genius in an academic powerhouse like Göttingen University, surrounded by the golden duo of mathematics. Hilbert and Klein weren't just famous, they were titans, and yet, they couldn't resist the magic of Noether's ability to make abstract formulas not just understandable, but engaging. At first, they may not have fully grasped her ideas. After all, she was a woman in a male-dominated field, and her focus on abstract concepts might have seemed a little too far out there. But over time, they recognized something incredible. Noether wasn't just brilliant, she was the one who could take abstract algebraic formulas and make them practical, even exciting. And this unique ability to blend rigor with fun was key to her later groundbreaking work, most famously, Noether's theorem. Let's talk about group theory. In mathematics, group theory is the study of symmetries and the rules governing operations. For many, it's an abstract and complex world that's hard to crack. But for Noether, group theory was her playground. Drawing inspiration from Hilbert and Klein's theories, she expanded her own thinking and started proposing fresh ideas that had never been considered before. Noether didn't just join in on Hilbert and Klein's research, she brought her own unique perspective, challenging their ideas and sparking intellectual debates. With their encouragement, Noether dove into group theory's core concepts, especially the connections between groups, rings, and algebraic structures. This would become the foundation for her later work, which bridged abstract algebra with the physical world, leading directly to the development of Noether's theorem. By 1915, Noether was collaborating with Hilbert and Klein, marking the start of her monumental contributions to mathematics. While she didn't immediately garner the fame she deserved, their support was crucial to her success. Hilbert didn't just guide her mathematically, he provided her with a platform in academia. Klein helped deepen her understanding of algebraic research. Their mentorship transformed Noether from a young researcher into one of the most influential mathematicians of the time. But working with such prestigious figures didn't make everything easy. Noether still faced intense prejudice from both the academic world and her colleagues. In a field dominated by men, her contributions were often overlooked simply because she was a woman. Even when she was collaborating closely with Hilbert and Klein, there were doubts about her abilities. Some may have whispered behind her back, questioning whether she could really contribute to such a high-level field. But Noether never let these biases define her path. Her focus, creativity, and relentless drive kept her pushing forward. Her breakthroughs in group theory, ring theory, and algebraic structures didn't just make waves in mathematics, they had a profound impact on physics as well. Her work, especially on the connection between symmetries and conservation laws, was vital to the development of quantum mechanics and relativity. Noether wasn't just a theoretical innovator, her ideas also provided the theoretical backbone for practical applications in science. Through her collaboration with Hilbert and Klein, Noether went from being a quiet scholar to the central figure in the mathematical world. Her ideas reshaped algebra and laid the groundwork for the future of modern physics. That partnership undoubtedly set her on the path to her greatest achievements. Without the support of Hilbert and Klein, Noether's work might have taken longer to come to light. But her relentless pursuit of knowledge ensured that she would find the breakthrough she was destined for. And just like that, Noether's journey from the background to the forefront proves that even when the world isn't watching, the right support can lead you to greatness. In 1918, Emmy Noether introduced a theorem that would completely transform the landscape of physics. This wasn't just a small discovery, it revealed the deep relationship between symmetries and conservation laws, forever changing the way scientists understood the universe. At first, Noether's theorem didn't create much of a stir, but it laid the foundation for much of the physics we know today. Simply put, Noether's theorem showed that conservation laws like the conservation of energy and momentum are directly tied to symmetries in nature. What does that mean? Well, Noether wasn't just talking about everyday rules like energy is always conserved. She showed that these laws were deeply rooted in the mathematical principle of symmetry. The universe's fundamental rules weren't just rules, they were linked to profound mathematical truths that governed everything from the smallest particles to the largest forces. By 1915, Noether had already started working with two giants of mathematics, David Hilbert and Felix Klein, diving deep into group theory and algebraic structures. These collaborations gave Noether the tools to link abstract algebra with the symmetries found in the physical world. Before her work, physicists knew conservation laws were crucial, but they didn't understand why they were so universal. Noether gave them the mathematical framework to answer that question. By the 1920s, Noether's theorem began to gain traction in the physics community. Her work became essential for understanding quantum mechanics and relativity, particularly when it came to translating the concept of symmetry into mathematical language. In quantum mechanics, Noether's theorem provided physicists with the tools they needed to understand the relationship between particles and forces. It was pivotal in the study of particle physics, especially when looking at symmetry breaking, one of the key phenomena in 20th-century particle physics. But Noether's influence didn't stop there. Her theorem also had a profound impact on relativity and classical mechanics. When Albert Einstein developed his theory of general relativity, the equations he created were deeply tied to the symmetries and conservation laws Noether had uncovered. Noether's theorem helped physicists better understand how gravity works, along with the relationship between matter and energy. By 1921, Noether's work began to reshape the foundations of quantum mechanics. Her theorem was critical in the development of the mathematical structure that supported quantum field theory and the standard model of particle physics. In fact, it was central to the study of symmetry breaking in particle accelerators, one of the most important areas of research in particle physics in the latter half of the 20th century. Even though Noether's theorem wasn't fully appreciated until after her death, its impact was already being felt in the 1920s. Physicists began to use it as a crucial tool in their research, especially in quantum mechanics and relativity. Noether's work provided a unified mathematical framework for understanding the universe, allowing scientists to predict and explain a wide range of physical phenomena through the lens of symmetry. The influence of Noether's theorem wasn't confined to theoretical physics, it had a significant impact on experimental physics as well. In particle accelerator experiments, Noether's work helped scientists design experiments and understand how particles interact, using symmetry to predict the existence of new particles. These experiments gave physicists the opportunity to test theories and push the boundaries of particle physics even further. By the mid-1920s, Noether's theorem was an indispensable tool in quantum mechanics. As quantum field theory and the Standard Model took shape, Noether's work provided the mathematical foundation for these theories. Her theorem helped physicists understand particle interactions and gave them the theoretical support needed to search for new particles. Beyond particle physics, Noether's theorem also played a crucial role in describing the universe's fundamental structure, including symmetry breaking. Symmetry breaking explains why the different fundamental forces of nature behave the way they do. Noether's theorem gave physicists a clear theoretical framework to understand these phenomena, helping them use mathematical tools to explain how the universe works at its deepest level. In short, Noether's theorem isn't just a piece of abstract mathematics, it's the key to understanding the very structure of the universe. From quantum mechanics to general relativity, her work continues to be the foundation for groundbreaking discoveries that shape our understanding of everything around us. And it all started with a simple but profound realization about the link between symmetry and conservation, one that still echoes in the theories that continue to change the world. If you think math is just a bunch of dry formulas, then you're in for a surprise. Emmy Noether didn't just conquer the world of mathematics, she practically transformed it. She wasn't just a mathematician, she was a magician in her own right, turning abstract, complex problems into clear and fascinating ideas. When you think of Noether's contributions, you might imagine a single theorem, but her impact stretches far beyond that. She unleashed a storm of innovation, especially in areas like group theory, algebraic geometry, modular theory, and invariant theory. By the 1920s, Noether was shaking things up, especially in abstract algebra. What she did wasn't just solve complex problems, it revolutionized the entire field. She didn't settle for solving problems within existing frameworks. Instead, she took abstract algebra and stretched it into the very foundation of modern mathematics. Noether didn't just introduce new theorems, she introduced a whole new way of thinking that still influences mathematicians today. Her work, especially in group theory and algebraic geometry, left the math world awestruck. Noether didn't just follow the existing paths, she broke out of the traditional frameworks and introduced new concepts and methods that revitalized the field. For example, her concept of the Noether group didn't just solve a major problem, it gave future researchers a powerful tool to study algebraic structures. This wasn't just a simple definition, it helped mathematicians understand the deep structures of group theory. But that's just scratching the surface. Noether's impact wasn't just about deriving mathematical formulas, her way of thinking became the theoretical foundation for entire areas of mathematics. Her work in invariant theory was nothing short of a big bang in the math world. Using the concept of algebraic invariance, she helped mathematicians tackle problems that were previously intractable. Her method was both simple and elegant, solving countless abstract mathematical issues. Noether didn't just stay in the realm of theory, her work also sparked practical applications in mathematics. Her abstract algebra thinking made previously incomprehensible theories useful for solving real-world problems. Suddenly, math wasn't just something written on a chalkboard, it became something dynamic, practical, and even beautiful. Imagine this, Noether's theorem wasn't just popular in the physics world, mathematicians also started chasing after her mysterious formulas. That's the magic of Noether. Not only did she provide physicists with powerful tools, but mathematicians began to study her work as well, trying to unlock even more of math's mysteries. Her innovative approach to abstract algebra gave mathematicians new directions to explore, like a key opening the door to the mathematical universe. Noether's contributions, especially in group theory, are practically irreplaceable in the math world. She helped mathematicians see algebraic structures from an entirely new angle, and her work in group theory provided a rich theoretical foundation for future research. Her Noether theorem became one of the fundamental theories in both physics and mathematics, still at the heart of countless research projects today. But Noether's legacy doesn't stop there. In the field of modular theory, her influence was just as immense. Her work on modular forms laid the groundwork for developments in algebraic geometry and number theory. Her research on modular spaces helped mathematicians understand the relationships between different mathematical structures, providing an important theoretical framework for both number theory and algebraic geometry. Noether wasn't just a mathematician, she was also an educator, a mentor who inspired those around her. Despite the many challenges she faced in the academic world, she still collaborated with scholars, sharing her groundbreaking research. She didn't just teach her students, she actively engaged in academic discussions, helping to push the entire field of mathematics forward. At the University of Göttingen, she left a lasting impression on her students, providing them with the inspiration they needed to develop their own research. In short, Noether wasn't just shaping math, she was reshaping the way the world understood it, bringing clarity and beauty to a once intimidating subject. Her work continues to inspire mathematicians and physicists alike, proving that the world of abstract ideas is not just for the few, but for everyone who dares to ask why and how. Emmy Noether might not be the most flashy star in the math world, but her life is full of surprising details and even a touch of humor. Her name might not be as famous as Einstein's, but her story is every bit as captivating, just with a different kind of magic, one rooted in the world of mathematics. Most people know Noether as a mathematical genius, but if you think she was the life of the party or a social butterfly, you'd be mistaken. In fact, Noether wasn't into socializing at all. She was rather low-key at social events, preferring to keep a low profile. Instead of mingling, she would retreat into her work, focusing on her formulas and theorems. If you bumped into her at a gathering, you might find her a little isolated, but that was just her way of staying focused, chasing the thing she loved most, math. She even considered socializing a bit of a waste of time. Yes, Noether was the type who would choose a tricky equation over a cocktail party. But here's the funny part: while her sense of humor may not have been famous in academic circles, she would sometimes drop a light-hearted quip in the classroom to break the ice. Picture this: as she's explaining an algebraic formula, she suddenly pauses and casually says, "This is a complicated equation, but don't worry, think of it as a math escape room. Let's see who cracks the code first." Her humor was simple but effective, much like her math: sharp, impactful, and a little unexpected. Noether's quiet, focused approach may have made her seem distant, but her humor, like her math, had a way of bringing everything together. She wasn't just a mathematician, she was an educator who knew how to make her complex ideas approachable, even fun. In her world, math wasn't just a series of dry numbers, it was a puzzle, a game, and sometimes, even a laugh. You might think that Noether's theorem is something distant, a concept far removed from your everyday life. But here's the thing: it's actually everywhere around you. Every time you use a quantum computer, Noether's theorem is playing a crucial role. Sounds crazy, right? But it's true. The technology you use every day, the research in modern physics, and even the basic laws of nature have Noether's fingerprints all over them. So, what exactly is Noether's theorem? In simple terms, it reveals a deep connection between symmetry and conservation laws. You might wonder, how does this relate to my daily life? Well, it all starts with quantum mechanics, particle physics, and even astrophysics. Noether's theorem provides the foundation for these fields. It helps scientists understand why laws like the conservation of energy and momentum are so universal. For instance, Noether's theorem explains why energy is always conserved in any physical system. The mathematical principles behind this are tied directly to her groundbreaking work. One key area where Noether's theorem shines is quantum mechanics. It helps physicists explain how quantum states change under different symmetries. Quantum mechanics is already complex enough, but Noether's theorem simplifies those transformations into a set of simple conservation laws. When you're working with a quantum computer, for example, its basic function relies on quantum bits evolving under symmetry, and that's exactly the kind of process Noether's theorem helps explain. Yep, the very foundation of quantum computing owes a lot to Noether. And let's talk about particle physics. Noether's theorem is practically a secret weapon for physicists. In particle accelerators and collision experiments, scientists use it to design experiments and predict how particles interact. Think about big experiments like those at the Large Hadron Collider, LHC. Can you imagine how scientists use Noether's theorem to analyze particle trajectories and energy exchanges in these high-energy collisions? In these experiments, Noether's work helps physicists uncover the fundamental forces of the universe, offering a mathematical explanation of how these forces maintain stability through symmetry. Now, let's take a leap into astrophysics. This might seem like the furthest thing from your day-to-day life, but it's actually connected to Noether's theorem, too. The conservation laws in the universe, like the conservation of momentum in planetary motion or gravitational interactions between stars, can be explained using her theorem. It's how astronomers understand the behavior of objects in space, especially under extreme conditions, like the formation of black holes or the expansion of the universe. Noether's theorem has already shaped our understanding of the cosmos, even in ways we don't always realize. You might even be surprised to know that Noether's theorem could help explain something as everyday as why you always seem to lose your remote control. It sounds a bit far-fetched, but stick with me. The way a remote control works, sending signals through radio waves, is actually tied to the principles of symmetry. Those invisible signals traveling through space? They follow the same conservation laws Noether identified, especially in terms of momentum and energy conservation. Think about it every time you use your TV, phone, or even browse the web. The technologies that make these things possible are deeply rooted in Noether's work. Her theorem didn't just help us understand the fundamental laws of physics, it fueled technological progress, enabling us to push the boundaries of science and explore the mysteries of the universe. Noether's theorem is not just something that sits in textbooks, it's alive and well, applied in every scientific experiment and high-tech invention we encounter. Whether it's the microscopic world of particles or the vastness of the universe, Noether's theorem serves as a bridge, allowing us to describe nature's most profound phenomena with a unified mathematical language. So, the next time you're working with quantum computers or analyzing data from a particle accelerator, remember to thank Noether. Though she may not be with us anymore, her ideas continue to light the way in science. Noether's theorem isn't just for the pages of textbooks. It's out there, making an impact in every corner of technology. And you, well, you're probably one of the many who are benefiting from it.
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.